Hey everyone, and welcome to this Forge College Explainer. I'm absolutely thrilled you're here today because I'll be your lead architect guiding you through the blueprints of moving your smart contracts over to Solana. You know, porting a contract isn't just a simple copy-paste job. It's really a ground-up structural redesign for a radically faster engine. So grab your coffee, temporarily forget literally everything you know about gas golfing, and let's get building. All right, let's jump right in. If you recall our previous lesson, tooling and a migration checklist for porting, we got our development environments totally aligned, we got our test hooks ready, and we strapped on our hard hats. We set up all those necessary guardrails. But now? Well, now it's time to draft the actual floor plans before we start tearing down any walls. Just to quickly anchor ourselves in the curriculum, we are right smack in the middle of our capstone project. We're officially shifting gears from that broader, high-level EVM mindset into the highly explicit, hyper-speed world of Solana contract design. Basically, we're moving out of the theory phase and into the concrete steps of mapping out your migration. So here is our architectural schematic for today. We're going to cover the moving day blueprint, core invariants, EVM versus Solana specs, setting boundaries, a quick code walkthrough, and finally, next steps. Okay, section 1, the moving day blueprint. Let's talk about how we safely dismantle an Ethereum contract and reassemble it for Solana. So, trying to move your contract over is kind of like stuffing a massive, fully assembled Victorian wardrobe into a sleek, ultra-modern modular apartment. You can't just shove it through the front door, right? You actually have to take it apart and know exactly how every single hinge works first. And in our case, those hinges are your invariants. Think of invariants as the unshakable laws of physics for your contract. We're talking about rules like balances must always conserve or a nonce must only go up. You literally have to sit down and imagine the absolute catastrophic nightmare bugs that would happen if these rules broke. Because honestly, if you don't know what core properties you're trying to preserve, your tests are going to be completely useless. Which brings us right into section 2, core invariants. To prevent those disasters we just talked about, and to make absolutely sure our end-to-end tests actually mirror a real production environment, we need a rigorous inventory system. Notice this 3-step scope checklist. You're going to apply this checklist to every single EVM function you plan to port. Step 1, identify the touch state, like what mappings or slots are you actually hitting. Step 2, classify the before and after invariants. And step 3, determine the minimal atomic unit needed on Solana to make this happen. Doing this creates a literal map that highlights exactly where your redesigns are going to be necessary. All right, section 3. EVM versus Solana specs. Let's compare the underlying models. Let's pull up the side-by-side engineering specs because this really illustrates the massive paradigm shift we're dealing with. Notice how the EVM allows arbitrary reads and writes from totally opaque storage owners? It's super flexible, sure, but it's hidden. It relies on what I like to call implicit magic. Solana, on the other hand, Solana is the ultimate bureaucrat. It relies on explicit bureaucracy. It demands explicit sized accounts and strict read-write borrowing flags declared up front, way before the transaction even runs. On the EVM, you just pay gas for whatever happens during execution. But on Solana, you meter compute units. That means you absolutely must avoid excessive deserialization of data you don't actually need. And as a nice bonus, the whole reentrancy surface area naturally shrinks on Solana simply because you have to pass accounts so explicitly. Moving on to section 4, setting boundaries. So with our invariants cataloged and our specs in hand, our next major workflow is deciding exactly how much logic actually fits through the door at one time. You've got to escalate your complexity step by step here. Try to map your EVM function to a single instruction if possible, because that's always going to be the fastest and cheapest route. But if you need dynamic accounts or cross-program calls, you might need to bundle it up into a grouped transaction. And if it's just way too big, or if it requires user agency right in the middle of the process, you have to architect a multi-transaction flow with really strict on-chain checkpoints. I can't stress this enough. Documenting these stepwise decisions is exactly what saves you from those dreaded logic races. By explicitly listing out your accounts, deciding your atomicity, and enumerating your signers, you ensure that no two instructions require mutable borrows of the exact same account in conflicting ways. It's all about planning the traffic flow long before you let the cars onto the highway. Okay, section 5, let's do a quick code walkthrough for a token transfer. Enough high-level theory, let's grab our magnifying glasses and actually look at a simplified anchor-style instruction handler. We want to see what this architectural blueprint looks like in real Rust code. Check out the account validation here. The has one equals owner constraint enforces an ownership invariant right at the program boundary. This is absolutely incredible because it validates the account before our handler even runs its first line of internal logic. It basically acts as an automatic bouncer standing right at the door of your contract. And building on those specs we talked about earlier, look at how authorization completely changes. On Ethereum, you have that implicit msg.sender just magically floating around in the background. But on Solana, you must translate those implicit Solidity authorizations into explicit runtime signature requirements. You literally have to write signer right in your account struct. You are telling Solana exactly who needs to sign the paperwork. No exceptions. Then, down here in the actual logic, we do something super deliberate. Instead of relying on EVM arithmetic exceptions to somehow catch a bad transfer deep into the execution, we perform a concrete balance invariant check early on. We explicitly abort if the from.balance is less than the amount. Why? Because we want to fail fast and fail cheap, way before we hit any expensive deserialization of other accounts. So as you map out your storage rights, you need to ask yourself this one question constantly. What is the minimal atomic unit needed to enforce your invariants? Seriously, write that down and tape it to your monitor. Asking this will ensure you're preserving your contract's atomicity without ever violating Solana's strict borrowing rules. Finally, Section 6, Next Steps and Blueprints. Let's roll up these blueprints and quickly review the core engineering principles we've covered today. Here are your key takeaways to memorize. Number 1. Inventory your invariants first. Figure out your unshakable laws of physics. Number 2. Map your atomicity early so you avoid logic races. Number 3. Make Ethereum's implicit assumptions totally explicit on Solana. And number 4. Treat deserialization cost as a first-class constraint. Making these actionable engineering decisions now will directly drive your account allocation and access controls moving forward. In our upcoming lesson, we're going to take today's inventory and boundary decisions and convert them into concrete account layouts and ownership models. We'll be deciding exactly when and where to use program-derived addresses to manage state. You definitely won't want to miss that one. So remember, what we're doing here isn't just a translation, it is a structural redesign for a radically faster engine. Are you ready to stop relying on EVM magic and start engineering with Solana precision? Thank you so much for joining this Forge College Explainer. Be sure to head over to forge.college to dive much deeper into these architectural blueprints and explore a ton of other amazing Web3 resources. Until next time, keep building and stay curious.